Welcome to lecture 9. That's the second lecture on simple harmonic motion. In the last lecture we talked about springs and Hooke's law in particular. Now I want us to imagine that we're doing the following experiment. I imagine I have a spring here and I'm going to connect it to this solid wall, or firmly screwed onto the table. I imagine the surface to be frictionless. Put a mass at the end of my spring. The mass can slide back and forth here. And the only force acting on it horizontally is going to be the force of the spring. Now I imagine I put a motion sensor here that I hook up to my computer. And this motion sensor is going to detect the position of this mass. If I don't have a motion sensor, because I'm doing this at home, I could imagine instead maybe I'm taking a video of this and I put a little ruler underneath so I can watch the position of the mass. And then I might later analyze that video frame by frame. So if I do that, so if I take this mass and I compress the spring, I let go and I watch what happens, here's what I observe. So the mass, when it's on this side here, squished, it's going to experience a force to the right. So it's going to accelerate. And it's going to accelerate, speed up, the whole time that it's going towards the equilibrium point. Let's say the equilibrium point is where I've drawn the mass right now. Now when it gets there, it doesn't just stop there, because it has momentum, it has velocity, it has inertia. It's right here. And the equilibrium point is the point at which there is no net force on the mass. So if the mass gets there and it's been speeding up the whole time, well, it's going to overshoot. Right? So it wants to, oh, equilibrium point, stop here, but too late, already moved past it. Now when it's over here, the spring is stretched. Right? So it's overshot. Now the spring is stretched, and so it's getting pulled back to the left. So it slows down, it's getting pulled back. In fact, the further it gets away from the equilibrium point, the stronger the force slowing it down. Gets to here, to a turning point, and it starts speeding up backwards. Getting faster and faster and faster until it reaches the equilibrium point. Okay, no net force, but oh no, it's going fast to the left. So it's going to overshoot again. And the same thing happens. It's going to overshoot. Now it's slowing down because it's moving left, but the spring that's now compressed is pushing it right. Gets here and it stops. It's here, stopped, but now it's getting pushed to the right. It starts speeding up again to the right. Faster, 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 faster to the equilibrium point. Oh no! We've got momentum, we've got velocity, we're going to overshoot again. And that keeps happening. And if there's no loss of energy to say friction, air resistance, it's going to keep doing that forevermore. It's going to go fastest in the middle, slow down on its way to the ends. Now if I do this now with the motion sensor, then I can actually track more precisely what happens. But here I've written down the observation that I just explained. Right? The mass accelerates towards the equilibrium point, it overshoots, it slows down, turns around, speeds back up, overshoots again, and so on and so forth. So let me now actually plot a graph of the position against time. And I imagine I want to say this is my x equals 0 point, and the x-axis is to the right, although it doesn't actually make much of a difference. So what is this going to look like? Let me draw a graph of position against time. Position x against time t. The units here aren't very important. Here you go. Using modern video editing technology, I saved you the terror of having to watch me attempt to draw something that has the right shape. So here you go. So I imagine I get these data points where I've tracked the position of the mass using my motion sensor, or maybe taking a video and having a ruler underneath and just tracking where the mass is. I get this here. Now we're eyeballing this, and I'm going to say it looks a little bit like a sine function, or perhaps a cosine function, right? Same shape, doesn't really matter whether it's sine or cosine. Also note I've started it as a positive x value, which strictly speaking suggests I should have started it over here, so I stretch it and let go. But I could have started it anywhere else. What I would get is this shape of this oscillation that, let's just say it's a sine function. Maybe I can have my computer sort of plot a best fit curve, and indeed I would observe that the sine function describes this fairly well. Now, so I might say, hey, what about x, the function of time? It's the sine of t. Now that's going to be wrong. That's not going to work. Why not? Because this function necessarily goes between -1 and 1. But my function might move further out. Nobody says that x is 1 equals 1 is the maximum. It could be x equals 20 centimeters. It could be x equals 2 millimeters. It could be anything. Right? Also, this would suggest that it takes exactly 2 pi seconds for this to go around once, but that's not necessarily true. So that function alone is not going to cut it, but it is a sine function, except we have to modify this a little bit. To do that, let's look at this in a little bit more detail. Let's define some terms. So this is my equilibrium point here. X equals 0, the time axis, that is my equilibrium point. The maximum distance that the mass is going to have, we're going to call that the amplitude. Actually, let me use a color here. I'm going to use blue. This is what we call the amplitude, A. And of course, on the other side, the amplitude is going to be the same. It's not, of course. I mean, that's an observation. Perhaps you could have guessed that. And we're going to see why later. But we observe the amplitude here is the same as the amplitude here. So in its oscillation, the mass moves as far to the right of the equilibrium point as it moves to the left of the equilibrium point. The next thing we can extract from this is how long does it take for one full oscillation. So for example, the mass might be over here, and I ask how long does it take from here to go all the way over there, go all the way back here before that whole process repeats. I can read that off from the graph very easily. It's essentially from here to here. That gives me a time interval, and that's of course called the period. T, same way you know the period from circular motion. Here we've got an oscillation. Again, it's a repeating motion, so we can talk about the period, the time before the motion repeats. So how can I incorporate those into my sine function? How can I make my sine function work out? Because this is clearly not working out. Well, if I have a sine function and I want to stretch it to have an amplitude of my choosing and not 1, all I have to do is to multiply the sine function by the value. So I might try something like this. X of t is a sine. Well, that's still not quite going to work, because that still says that the time from here to here, the period, would be 2 pi. In fact, I might worry that taking the sine of something in seconds, like, does it even make sense? So here's how we can accommodate that. Let me write down the answer. So we can imagine these as being kind of our trials. So try 1, try 2, and then now we're actually going to get the right answer here. A sine instead of having t in here, I want the motion to repeat after that time, maybe 5 seconds, maybe 1 second, right? Whatever the value of capital T, the period. So the way we can do this is in the following way. So I put in here, inside the sine function, into the argument of the sine function, I put 2 pi time over period. We can check that makes sense. Once t is equal to 1 period, right? So time is started here, tick, 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 tick. Okay, now we are at, this is 1 second. Okay, now we're at 1 second. Then this becomes 1, so the sine of 2 pi, and that's indeed 1 full rotation. Actually, We're not quite there yet, because a sine function would start down here. I don't want to start down here. I want to start up there. So what I can do is I can just shift my whole function left or right by adding a constant in here. And in this case, I want to add pi over 2. Remember, all of this is, of course, in radians, right? Why will this work? It will work exactly because if I have 0, right, I always want to be, the sine functions would start down here, but I want to be kind of 1/4 period pi over 2 ahead of the game, so I can just add that here. That's as it applies here. In general, I might not have pi over 2 here. If you just wrote it down in your notes, well, you can just write it again. But we just have some kind of constant we're going to call the phase constant. This just shifts the whole function left or right. The phase constant that shifts the function left or right. What does it mean? It shifts it in time. It's really a thing that you can choose by choosing your time variable appropriately. So if I wanted a sine function, I should have just started my stopwatch here, t equals 0 here, rather than here, for example. But this is the most general form of the position function of a sine function like that. Okay, so let me just write this out again, because we're going to write it down a slightly different way. So I'm going to write it is x of t, the position of my mass, is equal to a sine 2 pi. We had 2 pi t over tau. Let me write it out again first. And then plus phi 0. That's the phase constant. For the most part, we're not going to worry about it, because all it does is kind of change when we started counting time. It doesn't do very much for the motion. It doesn't really change the motion. The sine function looks the same. I can rewrite this instead of t, right? I can write the frequency. You know that from circular motion, a period is 1 over frequency. If it takes half a second to do one cycle, well, then I have 2 cycles per second. If it takes 5 seconds for one cycle, I have 1/5 of a cycle per second. So I can write this as a sine 2 pi f t. I'm going to keep the phase constant right now, though in the future we'll often not include it, because it doesn't do very much for us at this point. And then I can also rewrite this 2 pi f. We've met that before in circular motion. I can call this omega. It's sort of the number of, if one full cycle is 2 pi, right? And this gives me like the radians per second. Again, that's a concept we've met in circular motion. You can write this as a sine omega t plus phi 0. Now I could have written this whole thing out not in terms of sine, but in terms of cosine as well. In fact, then there would be no phase constant here at all. This would literally just be the cosine function. But again, if the function started somewhere else, say it started down here, it would just change the phase constant. Whether I use sine or cosine doesn't really matter, because those two functions in the first place are related by their phase constant only. So I've used sine. Maybe the textbook uses cosine. I don't know. I don't really care. It doesn't change anything. Okay, so that is the position as a function of time. Amplitude times the sine of omega t is omega 2 pi f, and f is 1 over t. Time for one full oscillation. So omega is a measure of the quickness of the oscillation, the rate of oscillation. And omega is, if omega is equal to 2 pi, then that means I get 1 full oscillation per second. If omega is equal to 4 pi, I get 2 full oscillations per second, and so on. So now I want to ask, how fast is this thing moving? Let's find the speed, the velocity rather, v as a function of t. Well, what is v? It's the rate of change of position, right? Now I have to use a derivative here because this is not a linear function, it's not a square function. This is a, it keeps changing, and its slope keeps changing, so I actually have to take a derivative. Now I take the derivative of this, you know how to do that, right? A sine becomes cosine, and the thing that multiplies the variable comes out front. The phase constant does nothing at all except it sticks around inside the argument. Of course, I could also write this in terms of f, the frequency over the period. Again, it wouldn't change very much. But you can see why it's convenient to have this, because then only one symbol comes out and not all these factors of 2 pi. Okay, so that's my velocity, and then I can also find the acceleration. And the acceleration too keeps changing, right? This is a cosine function, so it's also oscillating. The velocity is also oscillating. The same thing is going to be true of the acceleration. Cosine goes to minus sine, and another factor of omega comes out. And so cosine goes back to sine with a minus sign in front. Omega t plus phi 0. Should have, of course, said here explicitly that, write it like this, since at is dv dt. Right, this is what I'm using to work this one out. Okay, so I've got a position, I've got the velocity, and I've got the acceleration. And they're all sines and cosine functions. Now, if you look at this, what we notice is that, hey, the acceleration and the position, they're both literally sine in my case. Velocity is cosine. Could, of course, all be the other way around if I started with cosine here. But then those would be cosine and this one would be sine. In our case, sine function, AA. So what I notice is that A as a function of time is minus sign here but not there. There's an omega squared here and not there, but the A sine omega t plus phi naught, that's the same here. It's minus omega squared times the position. It's just a curious observation in a way, but actually it tells a bit more of a story, because we know that the acceleration as a function of time is equal to the net force divided by the mass by Newton's second law, NL2, Newton's law number 2, right? What is the net force? Well, the system we're looking at is a mass on a spring. So the net force is just given by Hooke's law minus kx. Right, so I can write this as minus kx over m. Oops, you can't see this at all, can you? Minus kx over m. This is by Hooke's law. So that's interesting. We've got two expressions for the acceleration in terms of x. Because this is a function of time, because x itself is a function of time. Right? So I've got that from the kinematics, the mathematical relationships between velocity, acceleration, and position. From the kinematics, I get this. From the dynamics, from Newton's second law, I get, and Hooke's law, I get this. So I can compare. So the only thing that can both be true is if omega squared is k over m. Right? Minus minus xx, well, omega squared has to be equal to k over m. Right? So we write this down again so we can follow the logic. So A is equal to minus omega squared x. It's true for all times. Function of time. We just compared the functions, found this to be true. And A is equal to minus k over m. X is a function of time. So the only conclusion is that omega squared is k over m. Omega is equal to the square root of k over m. So what was omega? Omega was the rate of oscillation. To make this more explicit, I can write the frequency. The frequency is omega over 2 pi. At omega equals 2 pi f. So that's equal to 1 over 2 pi times k square root of k over m. And I can also find the period. The period is 1 over f. So that's equal to 2 pi times the square root of m over k. Right, flipping those. Let's look at this. Does this make sense? Well, if the spring is harder, it's a more solid spring, harder to squeeze, applies more force, then it's going to push back faster, push back more. So bigger K means that the frequency is higher, more oscillations per second. Yes, I think that makes sense. The period, meanwhile, gets smaller if K gets bigger. Again, if the spring is stronger, then I expect the oscillation to take less time because it takes less time to slow down the mass in the first place. On the other hand, if the mass gets bigger, then the system's going to have more momentum as it goes through the equilibrium point. It's going to take more work to slow it down, and so I expect it to take longer. And we can test that in the experiment to confirm that relationship. Okay. So let's just make one more comparison here, and one more sort of piece of information that I want to include here, and that is I want to make that relationship between circular motion and oscillatory motion, this so-called simple harmonic motion. It's a term used for these sinusoidal position functions. I want to make that relationship more explicit. So let's compare it to circular motion. It uses the same symbols, period, frequency, angular frequency or angular velocity, and they mean the same thing. Right? The time for one full oscillation, for one full cycle, how many cycles per second, and then how many, if 2 pi is one full cycle, then how many of those, let's call them radians, do we get, right? So the difference is, it's not, in this case, it's not literally a circular motion where omega tells me the change of angle per second. Instead, omega tells me the change of the argument inside the sine function, which of course is in radians. Right, so it's almost as if there is some kind of angle that represents the position of the mass on the spring. We call this thing inside the argument, we call that the phase of my oscillation. This thing here was the phase constant. It's the piece in here that stays constant, but the whole thing together is what we call the phase. So let's make that now more explicit. And the sort of experiment you can imagine you might do is the following. Imagine I have a light over here, kind of big spotlight shining a beam of light this way. Now over here I have an object, a ball, that's moving in a circle like this. Uniform circular motion. So what does uniform circular motion mean? It means that this angle here, let's call it theta, theta is going to change at a constant rate. It will increase linearly. Let's keep growing, 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 growing. Yes, it reaches 2 pi, but then it just keeps growing. Even if 3 pi corresponds to the same position as 1 pi, it still has moved the total angle of 3 pi once it's 1.5 times around. And omega here is constant. Right, no angular acceleration. That's why it's uniform circular motion. Now, if I imagine doing this and I have a screen back here, I can watch the shadow. Right, and the shadow is of course going to form right here on the wall behind this ball. If I track the motion of the shadow, that shadow is going to undergo simple harmonic motion, the motion of the oscillation that we just discussed. So the shadow undergoes simple harmonic motion. Simple harmonic motion just meaning sinusoidal motion, as we've described. Why is that? Can I justify that statement? Yes, I can. What is the height of this? If I just care about the vertical component of this. Let me zoom in over here. Let's imagine it's here. The shadow doesn't pick up how far left or right this object is. Right, I assume the light is sufficiently far away that the light rays essentially come in parallel. This vertical component here, the y position if you like, let's make this x, let's make this y, this angle is theta, well, y is equal to the radius r sine theta. It's the opposite, and this radius is r. But we just said theta is a function that's linear in t, with the constant of proportionality being omega. So I get that y is r sine omega t. That is, of course, simple harmonic motion. Whereas the phase constant, well, I could have included a sort of starting angle here at time equals 0, where is the object. If there's nothing added, we assume it's at 0 theta, but I could have added something here. It would have appeared in here as well. I would get exactly the same expression that I had above. That is the basics of simple harmonic motion. The rest is applications, and I'll see you in class for those.